So we looked at the idea of if the curl of a vector field is 0, then it might be conservative, but not necessarily. But that's useful because we can easily say that if the curl is non-zero, then we know that it is not conservative. But if we add a little bit more to this previous theorem, then we can actually make a determination whether the vector field is conservative based on the curl being 0. So here's another theorem. If this vector field, if f is a vector field defined on all of 3 space whose component functions have continuous partial derivatives, and this is what we're kind of adding here, these component functions having continuous partial derivatives. So if I have this thing and it's defined on all of 3 space, then if the curl is f or 0, then we can say, hey, this vector field f is in fact a conservative vector field. So what we added to it is defined on all 3 space and the component function having continuous partial derivatives. We added that. Now under those conditions we can say that if the curl is 0, then the vector field is in fact continuous. So let's just consider for a moment. Let's let f be equal to y x z. Let's see, the partial of y with respect to x is going to be 0. The partial of x with respect to y is going to be 0. The partial of z with respect to z is 1. Okay, so this vector field is obviously defined on all 3 space. I'm looking at the partials, and these partials are continuous. There's no discontinuity here. So I have these first conditions met. So now all I really need to do is figure out what the curl is. So again, I'm thinking about this as being P, Q, and R. And for the curl, I need this del operator cross F. I need the determinant of that. And that's going to be I, J, K. And then I'm going to have the partial with respect to x, partial with respect to y, partial with respect to z. And then this is, of course, y, x, and z. So this determinant is going to be the partial of z with respect to y minus the partial of x with respect to z, I, minus, let me see, that was I, so j, this is going to be the partial of z with respect to x minus the partial of y with respect to z, j. And obviously to write this in the standard form for the curl, I would factor out this negative, but I'm not going to bother with that for right now. And then I'll have the partial of z with respect to x minus the partial of y with respect to z, okay. So that gives me, let's see, partial of z with respect to y. Well, this is x, y, and z, so this is going to be 0 minus 0i minus, this is going to be 0 minus 0j. Let's see, plus z with respect to x is going to be 0 minus y with respect to z is 0. Okay, so this equals the 0 vector. So the curl is 0. Now, since we have these other components satisfied, I can now say that f is conservative. Now, if f is conservative, then I should be able to find the function little f such that cap f equals the gradient of little f. All right, I should be able to find this potential function. So let's go ahead and work through that here real quickly. Now, I'm going to write this up here again. F equals a function was y, x, z. So I know that the partial of f with respect to x has to be equal to y. That implies, see, the integral of y dx equals xy plus, I'm going to call it g, which could be some function of what's left, y and z. Now if I take the derivative of this, if I take the partial of this with respect to y, because this is x, y, and z, p, q, and r. So I take my next partial. So the partial of f with respect to y is going to be x plus this partial of g with respect to y, which again is a function of y and z. Now when I look at this, my partial of y has to be equal to x. That tells me that this partial right here has got to be 0. So therefore, this partial with respect to y of yz has got to be equal to 0, which means it could just be a function of z. So right now where I'm at is I'm thinking based on these first two partials, the f right now is going to be equal to xy plus some function of z. So if I now take this partial with respect to z, what I get is 0 plus h prime of z. Now notice this can only be a function of z. If this was a function of x or y, when I took the partials, they would have shown up earlier, and they didn't. So what is the partial with respect to z? That is simply equal to z. That implies that h prime of z must be equal to z, which then tells me that if I integrate this, I need to integrate z with respect to z, and what I get is z squared over 2 plus some constant of integration. So now when I put all these pieces back together, what I end up with is this potential function f, which is a function of x, y, and z, is simply going to be xy plus z squared over 2. Now this c, it doesn't matter, it's some constant, so I can take it to be 0, simply because as soon as I start taking partials, it doesn't matter what the constant is, it's going away every time. So as a really quick check, let's make sure we didn't screw this thing up. Let's just find the partial of f with respect to x. That's going to be y, that's going to be 0. The partial of f with respect to y is going to be x. And the partial of f with respect to z, that part's going to be 0, that's just going to be z, which is equal to this gradient function f, which was y, x, and z. So we confirmed that f is in fact conservative, and then we went out and found the potential function such that f is equal to the gradient of little f.